Wonderful world of derivatives. So let's start with displacement here. Now, what is displacement? All right, so displacement is just the distance, all right, that something has already traveled, right? So let's say this is 5. The displacement between these two objects is 5. If it goes this way for 5, it's still 5. Okay, velocity. All right, so that is that's like meters per second. That is it's a rate, so it's changing. So if this ball covers this distance in 1 second, then its velocity is going to be 5 meters per second. Okay, acceleration. What's that? All right, so the unit would be meters per second, and that's because its rate is changing. So it might be going 5 meters a second, but then at the next second, let's say the ball goes another 5 meters, okay, so 5 meters, but this time it does it quicker. Let's say it does it in a half of a second, so 0.5 of a second. Well, now its rate is not 5 meters a second, its rate is 10 meters a second because it just covered the same distance in half of the time, okay? So you could say that the ball has accelerated since it left its initial position, so accelerated. All right, so when you take the derivatives here, you're going to start with like an acceleration style equation, which is 2x squared. Now you take the derivative of that, you're going to get a velocity, all right? And if you take the derivative of velocity, you're going to get a displacement, right? There it is. Now another thing that's important to know when you're thinking about derivatives is instantaneous rate of change. Now what the heck is that? That is like, for instance, for displacement, an instantaneous rate of change would be constant. There would be no change. It's not increasing or decreasing because it's already there. It's more of a statement. You're just saying, I am at 4, not I'm moving. I'm already there. That's displacement. Velocity is moving. So if you look at its graph, you can see it's constantly going up. It could also be constantly going down. Okay? So it's increasing or decreasing at a constant rate. So this 5 meters per second is a velocity, all right? Now acceleration, it's increasing at an increasing or decreasing rate. Now that's a little bit harder to understand, but you can see how the graph kind of curves up and you can see how the rate changes. The rate is not constant all the time. You can see that it's gonna reach a higher point sooner than the velocity graph because it's accelerating. So like I was saying over here, if the ball gets to here at 5 meters a second in 1 second, then it gets to here in half of a second, then it has accelerated as compared to the first stretch here. So it's a little bit harder to understand, but if you're really thinking about it, the unit is meters per second. So you're going to have a velocity here, right? Because this is velocity if you just look at the top half, right? And then the second per second means it's changing every second. So, or less, it's really instantaneously changing. Every millionth of a second, it's changing. It's never the same, constantly changing. So, meters per second, just the top half, is a velocity. Then you look at the second half here, and you can see that every single second, it's going to be different, either increasing or decreasing velocity. And so that's it.
We were talking about the derivatives earlier, as my fellow student Blaine was saying. And with derivatives, the most important concept that you will get is the power rule. So what is the power rule? The power rule just states that the limit, the change of x, or delta x, as it goes to 0, and the formula is f, parentheses, x plus delta x minus f of x over delta x. And what that's really explaining is this formula right here, which means that if f of x, so an equation of x, is equal to x to a certain exponent that does not equal 0, which means that if you take the derivative of this equation, and this does not equal 0, you will get here, this n will go in front of the x and be subtracted by 1. And that gives you the instantaneous rate of change. So as you can see here, I already have written. Anyways, I was saying f of x equals n of x to the n minus 1. So what I showed here is the n went down, and this has to get subtracted. So let's put in 2, for example. So we have f of x equals x squared, which is right here. what really happens is the 2 comes down, and that 2 gets subtracted by 1, which gives me 2x to the 1, or just 2x. And I have another example over here. So this one actually has a bigger number, and it's a negative, just to show the concept of it. So this negative 100 gets moved in front of the x, which is shown here, and then it gets subtracted by 1, which is shown by this part right here. So your final answer for taking the derivative or the instantaneous rate of change for that section is negative 100x to the negative 101. Over here we have a little bit more complex of an equation. So we have the g of x equals x to the third, and we take the derivative of that to get 3x to the 3 minus 1, or 3x squared. And finally, I decided that it would be a great idea to put a decimal in here. So I have z to the x equals x to the 2.5. And what happened here was, I accidentally wrote plus 1. Anyways, they get subtracted by 1, so the derivative of the equation zx equals 2.571 to the x. And that same 2.571 minus 1, which would equal a positive 2.571x to the 1.571. And we're going to have an intermission until I get to my next concept. Back to the wonderful world of derivatives. We had a short recess. I am very sorry about that. We went uptown, we had a cheeseburger, we petted a cat as we walked out of the grocery store, but now we're back. So anyways, what I have here is a beautiful graph. And what we're going to do with this beautiful graph is we're going to plot an interval of the derivative of where it is greater than 0, of course. So this is the graph, f of x. And we are going to plot an interval where f of x prime is greater than 0. So we know now, after Blaine's explanation, that when you get the instantaneous rate of change, or a derivative, or f prime in this case, your instantaneous rate of change can also be taken by the slope. So slope is the m in y equals mx plus b. Well, it's this whole section right here. So, for example, people say, no, y mx plus b is the whole slope. No, that's just the equation of a line. So this right here. And for example, we have a beautiful graph right here. And this graph is just going to be a 2 by 2. And if we have a line like this, the slope of this line is y equals x. So we can see that, or you can plot it like this. The slope of this line is also 1 because it's rise. So the rise over run, which is 1 over 1, which is 1. Anyways, so for this one, practically, the derivative of this one would be a line at 1 going straight. And that's the derivative of this equation. So for this equation, we have to find a place where it is greater than 0. And some of you might say, okay, it's greater than 0 right here and above over here. Well, technically yes, but the derivative not so much. Since the derivative is actually slope, we know that from here to this point right there, the derivative would be negative.
Okay.
So, as I was saying, this is negative slope, because from here to here, this is negative, so the derivative is negative. And if you take it just at this little point, your derivative would be 0. So that one's not it either. But if we look at from here, so from here to here, we can tell that is a positive slope on this graph. So therefore, since this is a positive slope, the derivative of f of x prime from this point to this point would be positive, even though in this section it is in the negative, but the derivative, as I keep explaining, will be positive. So therefore, you could plot a point here, 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 here. You can even plot a point right here under this x graph. So it's technically negative, but the derivative is positive. And, well, that's all we can do for you folks. Have fun in AP Calculus, and this is the wonderful world of derivatives.